Dear audience, welcome to my YouTube channel. Today I will talk about how to implement a selection sort with Nand2Tetris assembly code. So let's have a look. What is selection sort? Selection sort is a technique to order all elements in a given array. First thing, we select this element as a reference and compare the next element to it. Compare the next element. If the next element is larger than this reference element, we do nothing. We then compare the one after until we found some element with value smaller than the reference. Then we do a swap. The second diagram shows the situation after swap. As you can see, minus 22,000 becomes here. And then we shrink the sort space to these remaining 3 elements and use the second element as a reference compared to the next. 4 is larger than 1, so we do not swap. And then compare minus 20,000. That's the case. Minus 20,000 is smaller than 1, so we do a swap. Swap here. We keep repeating this process until we reached the sub-array only has 1 element. Then we stop sorting. Here's the resultant array. It is sorted in an ascending order, from smallest to the largest. The technique we are using is still TDD, test-driven development. If you don't know what is TDD, please have a look of our first video. You will see a link appear over here. Okay, the test cases used here is exactly the same as array min, finding the minimal element in an array as we saw it in the previous video. Here's an implementation specification. The starting address is stored in RAM1, and the size, for this case the size is 4, and we assume the starting address is 1000. When finished the sorting, let's put a true to RAM0 to indicate we have done. So the question is, can we reuse the code from array min to implement this selection sort easier? Recall that array min is an algorithm finding the smallest element. It involves comparing 2 elements. So in selection sort, we are also comparing 2 elements. So let's reuse the array min code. Okay, where's our array min code? Our array min code is here. Let's just copy array min test, array min ground truth compare file, and ASM file. Let's copy those 3 and to our selection sort folder, paste, and rename. Let's rename this to selection sort. SelectionSort.txt. Okay, let's open them up. Use VS Code. Open folder. Documents, GitHub. Nand2Tetris ASM example. SelectionSort. Okay, open this folder. Open this. SelectionSort. We need to modify this name to SelectionSort. SelectionSort. Okay, I think everything else are the same, are unchanged. Let's open up the ground truth. We need to manually modify this ground truth to an ascending order. 1, 2, 3, 4. What is ascending order for this? Let's manually sort this one. What is smallest? 1, 2, 3. There are two number 3 over there. 5, 6. 1, 2, 3, 4, 5, 6. Is there a 4? Yeah. 4 should be here. So here's our answer after sorting. Let's copy it over here. 1, 2, 3, 3, 4, 5, 6. Four zeros. After sorting, still 4 zeros. No difference. -2, -1, -4, -3. 4, 3, 2, 1. 4, 3, 2, 1. Yeah, that's it. And for this one, minus let's copy this. Manually sort this number into order. -3 is the smallest. Cut, paste. 1, 4. Yeah, that's it. -3, -2, 1, 4. For this one, copy this to here. 1 for 20,000 32767. $20,000. 32767. What's next? I think I can do this. Cut, paste, paste. Yeah. Cut, paste, and to cut this as well. After 1 and 4, that's positive 20,000 minus 20,000. Yeah, I think that's already in order. Don't need to do anything. We use true to indicate after sorting is finished. True is -1, so let's replace all those are zeros with -1. Four, five, six. That's it, our ground truth file. Save and close. Don't have to. What else do we need to do? Set 0, set 0. 0 means false, not finished sorting. Yeah, I think that's it for the test script. Let's do implementation. The next step is to implement our selection sort algorithm. Let's do the easiest thing first. Finish at R0 m equals -1 to indicate we have finished. So let's change all the at end to at finish. We can remove this part because we are using the first element as a reference instead of an absolute maximum. What is this? This is calculating the finish position. What we need to do is save. We can still use this. We can still use this. But in addition to R1 and R2, we need to use R3 as an inner loop index, and keep using R1 as an outer loop index, R2 as a last element. subtract start from 0. So the last element is array 0 plus length minus 1. We can keep using this part, no difference. We need to make a copy. Add 1. Use R3 as the there should be 2 nested loops. We can remove this part. This is the outer. Let's say this is the inner loop. Outer loop. And change this loop to inner loop. Within the outer loop, each time we increment the output, the outer loop index by 1. At 1. Should take this out. If the outer loop index reaches the last element, then we terminate. And put -1 in R0 to indicate we have finished. Check terminate. Let's see, for inner loop, what do we do? Dereference R1. What was R1? R1 is a reference. Called element, I should call it 3. Inner index 2. That's my drawing. In this case, our outer loop index R1 is this reference element, and the inner loop index R3 is this moving element. R3 is same as, should be D plus 1. Should always have this. This should put into the inner, the outer loop. Put into the outer loop. Put it here. Something weird. Control P. Tab. Display tab. Why it doesn't? Okay. It is mixed use of tab and spaces. Let's make sure it all use tab. Let's Control H. Control F. Replace with come to this. Why not replacing? 1, 2, 3, 4. Okay, now they're all using spaces. Where we are? R1 equals R3 equals R1 plus 1. Yeah, the setup index. Inner loop. Now D contains the value of reference element. Not a reference. I mean the inner the element pointed by the inner index. Element pos. If this number is positive number, jump to element pos. Let's rename this. It has REF. Instead of add R0, we should add R1. because we use R1. Maybe need one more step. R1 is a pointer. We need one more step. A equals M. If we do not do A equals M, what we get is the address of this element, which is 1000. But what we want is a value inside this memory address, so we need one more step to dereference. Okay, jump to here. R1 dereference R0. No, here should be R3. R3 is a inner loop index, which is the current element we are looking for. The inner index, which is this. Outer index is this. We dereference we should dereference R3. This is R1. R3. Jump to here. Reference is R1. No problem. R0. No, here should be R3, and here R1. A equals M. Subtract. Okay, that's fine. Update. Instead of call it update, I would like to rename it as a swap. Because previously we do update just copy the current element's value to R0, but this time we need to swap the two values. Swap dereference one A equals M. Before we overwriting R1, we need to define a temp variable. At R1 get its value. A equals R1 equals M. D equals M. Dereference R1 is a pointer. If it is a pointer already pointed into a dereference again. M equals D. Let me have a think. It is a 1000. R1 at R1. Yeah, we need to dereference. Because after add R1, the current after executing this instruction, what inside A is just 1, RAM 1. We need to dereference that to get pointer address, then dereference a pointer address to get a memory value. Yeah. 16. Yeah. To reference R3 into D, R1, R3 give R1, and R1 give temp. The next will be at temp D equals M, and then at R3 A equals M equals D. Yeah, that's swap. Skip means do nothing. Do nothing, we need to increment the inner index. The inner index is R3. Jump to inner loop. We need to check the inner loop reached the end. Check the inner loop reached the end. Which means R3 equals R2. Should define a inner finish. Once inner finish, what should we do? Increment outer index. M equals M plus 1. And at outer loop. At outer loop 0 JMP, 0 jump. Increment the outer index and jump to outer loop, which is here. Check terminate. R1, R3 always start from D plus 1. Always from outer loop plus 1. Skip the swap. R3 increment. Jump back to inner loop. Inner finished. Where's the inner finished? Okay, should be here. At inner finish D GGT. R3. Okay, let's try if this works. SelectionSort. Open terminal. CPU emulator.sh. Let's load this array min SelectionSort.test. Can we do it correctly? Fast. Oh, failure at line 2. What happened? It seems it didn't reach the end. Let's see how it's going. 1, 2, 3, 4. This is default. It means the program didn't hit the end. Let's just increase this clock cycle to 500 and see how it goes. Because resorting involves a lot of comparison and swap and a two nested loop. It is expected to take longer time, take more clock cycles than the array min. Where's my CPU emulator? Let's see if this could execute to the end. Yeah, it seems to pass the first test. Of course, failed here because we still have a 200 clock cycles here. Let's modify everything to 500. Let's reload the test script because we just modified the test script. We need to load script every time we have done modification. Output. Turn off animation. Comparison failure at line 4. So what happened? Oh, this is that long array. That long array with 7 elements. So let's give this even longer clock cycles, 1000. To reload test script. Comparison failure at line 10. What is line 10? Line 10. Ground truth. Line 10 is this line. We can see minus 1 4. Here it reached the end, but why this minus 32768 didn't appear at the front? Okay. That's the second last test case. Second last, which is this one. 2000 1 4 minus 32768 minus 32768. Why? What happened? Not sure what has happened. Let's isolate this test case. Nand2Tetris. That's line 9. Line 10, where we have 11. 1, 2, 3, 4. Oh, okay. Including the header line, that's 11. No problem. Copy this over to here. We also need to copy the output list. Paste it before the test case. And we need to also isolate the ground truth. Nand2.cmp. Copy the entire thing and remove everything else. TST should call it SelectionSort, no problem. Cut line 10. Line 10. Let's execute this line 10 test script. Let's see what happens. Data flow. Four, three, one. Too much detail. Just a program flow. Inside the temp is always 20,000. Here, add up this end. Go into the inner loop. R3 equals R1 plus 1. D equals D minus 1. Let's put this code side by side. Where is this? D equals D minus M, which is here. At line 47. Jump. Do not jump. Enter. 1. this R3. Eh? Where is this? 3. R3 A equals M. R3 equals M is here. R3 equals M, D equals M. At 72. Jump to here, jump to here, because the reference is positive, which is R3. R3, this is positive, so come to here. No, D should contain 1. Eh? Yeah, D contain 1. Oh, here should be R1, because before jumping to here, what we checked is R1. R3. Oh, here should be R1 instead. R1 is a reference. R1. Okay, fixed. Let's try to run the entire test again. No animation. Start. Okay, that's it. So our selection sort is finished. That's it. Today's video. Thanks for watching. I will upload my test cases and the implementation to my GitHub. See you next video.